Learning objectives for lecture 2 are to design variable control charts to analyze a business or manufacturing product. Analyze a variable control chart to detect when the process is in control. The reading assignment is chapter 6, pages 235 to 253. So we talked about in the last lecture about sampling. Sampling, we go out to an assembly line and we select representative sample from the population. Maybe we're manufacturing automobile tires, and we can manufacture maybe 100 a day. Well, every hour on the hour we go out and we select 3 tires off the assembly line, and those three are what's known as our subgroup. So let's talk more about a subgroup and how do we do that? So the big thing here is when you're selecting subgroups is that the subgroup contains a unit that's created under the same conditions. It's a snapshot of the process. They should be taken close together in time, but still be independent of each other. So you wouldn't want to. So for example, if we had our assembly line making tires, and if we select one tire off the assembly line and the machine breaks down and then we have to repair it, we get it back running, then we select 2 more tires off the assembly line. Those 3 are in a group because the situation's changed, right? We've adjusted the machine, so we have to be careful selecting our groups. We want them to be close together in time and taken under similar conditions. So how many subgroups should we use? Well, when you're initially setting up control charts, subgroups of 4 or 5 collected every hour are pretty common. Then as the process demonstrates stability, or as improvements are made, you can maybe decrease the frequency. Maybe you do them every other hour, or every shift you select a sample from the population. Basically, you want to collect subgroups for a duration that's long enough to ensure that the major sources of variation have the chance to occur. So usually 100 observations or more is enough. So for example, 25 subgroups with 4 observations each. So maybe we take 4 tires off the assembly line, and we do that until we have a set of 100 tires analyzed. So and the reason why we want to do this is select these subgroups because we want them to be what's known as rational subgroups. They're produced under the same conditions. So this little chart shows you what I'm talking about. So here, for example, these are 5, but let's say we have 5 tires we selected here in our subgroup, produced all under the same kind of conditions. Well, the next hour you select 5 more, right? The things might have shifted a little bit, but these tires are all measured under the same conditions. And then the next hour you take 5 more tires. So here, when you're talking about variation, you're going to have variation between subgroups. That's normal. You can also have variation within each group. That's also normal. So here, I showed you the equation for the upper control limit for the X bar chart here. Notice it has the range value in here. So the X bar chart is affected by the range, and so that's why you want to make sure you're taking these subgroups close together, so you don't get this. You want to try to minimize this R value. Really, is what you're trying to do here. So we got a chart plotted. What do we do with it? Well, there's a lot of different theories on exactly what to do, and this process has evolved over the time. Back in the 1920s, when Shewhart actually came up with this, he basically, had one primary rule, and that's what's known as Rule 1 now. And Rule 1 says that, if one point is 3 or more standard deviations from the mean, so here's our control chart, here's our mean, and we got, the upper control limit is 3 sigmas above the mean, and the lower control limit is 3 sigmas minus below the mean. So here we have 2 points that are plotted beyond the 3 sigma value. So, this is out of control, obviously. Uh, and as time went on, people, added more rules to this basic set. This is the basic one here. Rule 1 is certainly, but over time, since 1920, as other engineers and have looked at this kind of situation, we've added additional rules. And so what I'm going to talk about here is the primary 4 basic rules. There are others. There are if you look at some advanced kind of control theory textbooks, there's probably about double that if you really want to get down to it. But these 4 will serve us well in this class, and certainly they encompass the majority of cases you're going to run into. So Rule 2 says that if 9 or more points in a row are on the same side of the mean. So here, for example, you have here's the mean, and you have 1, 2, 3, 4, 5, 6, 7, 8, 9 points all plotting above the mean. Well, that would be unusual. I mean, because again, there's something causing this. Even though these points did not exceed the 3 sigma level, if you get this many points plotting above the mean, something has changed. Maybe a new operator's come on board. Maybe there's the machine's starting to wear out. All kinds of things can cause this, but this is obviously some reason causing this. This is not natural variation. So what should you do? You should investigate and see if you can figure out exactly what's causing this kind of situation. Rule 3 says if 6 or more points in a row are continually increasing or continually decreasing. So here you have a case where, again, you didn't have a point that exceeded the 3 sigma or the minus 3 sigma, but you had a case where you have what's known as a trend developing. This is also would be very unusual. This is not natural variation. Something's causing this kind of situation. So here, this would be classified as an out of control process. You need to investigate to figure out what's causing this. Rule 4 basically says, if you have 14 or more points that alternate in direction, increasing and then decreasing. So here, for example, you have this point that's above the X bar, the next point's below it. Then it goes back above it, then below it, then above it and below it, continually for like 14 more points. So oscillation is much more than noise. Noise doesn't cause this much kind of oscillation. So each of these kind of cases is a point where these 4 rules we're going to apply. So as you run through the case studies and the problems, keep these in mind.